Good morning, LS and GS student. This is my math teacher. Miss you all. This is the 6th week of quarantine. Our lesson today is about lines and planes. In fact, today we are going to learn how to determine the parametric equations of a straight line. In fact, the parametric equations of a straight line, you saw it in grade 10. It was of the form x equal alpha t plus x of a and y equal beta t plus y of a, where t is any real number. This year we'll add, of course, the elevation because we are working in space, 3 dimension. So it will be as in the form of x equal alpha t plus x of a, y equal beta t plus y of a, and in fact we'll have z equal gamma t plus z of a. If we have first of all a straight line D and we have 2 points A and M on the straight line, in fact A is a fixed point and M is a variable point on the straight line D, and R is a director vector of the straight line. We know that a director vector of a straight line is held by a line parallel to D, or this vector is on D, lies on D. Now, since R parallel to D, then we can say that the vector R and the vector M are collinear. By the way, a straight line admits infinity of director vectors, because any vector held by a line parallel to this straight line, then it is a director vector of the straight line. If two vectors are collinear, you remember that they have the form u equal kv. So in this case, since AM and R are collinear, so I can write AM equal TR, where T is any real number. So by using the coordinates, we know that the vector AM, its coordinates x minus xa, y minus ya, and z minus za. Then we have here x minus xa equal alpha t. I'm going to put x in the second side of the equation. So we obtain x equal alpha t plus x of a, y minus y of a equal bt gives us y equal beta t plus y of a, and z minus z of a equal gamma t, of course, z equal gamma t plus z of a. Sorry, here must be a capital letter. So in this case, what we can say, then the system of parametric equations of the straight line D is given by x equal alpha t plus x of a, y equal beta t plus y of a, and z equal gamma t plus z of a. By the way, alpha, beta, gamma are the coordinates of the director vector. Here they ask us to determine the parametric equations of the straight line D passing through the point A and whose director vector are equal to minus 4 and 1. In fact, 2 is alpha. From the preceding result here, I have alpha, beta, gamma are the coefficients of T. So here I have 2 is alpha, minus 4 is beta, and 1 is gamma, as you notice here. So I can say that the parametric equations of the straight line D are of the form x equal alpha t plus x of a, y equal beta t plus y of a, which is minus 2, and z equal gamma t plus what? Z of a. This question is for you to practice. We have here another example. They gave us the straight line D of equation, parametric equations in fact, x equal to m plus 1, y equal minus m, and z equal to m plus 5, where m is any real number. They ask us to determine 3 vectors of D. In fact, as I said before, if a vector is held by a line parallel to the straight line is a director vector, then any straight line admits infinity of director vectors. How I can determine the sum of the director vectors? Usually we determine the first director vector, then any vector collinear to it, it is also a director vector of the straight line. And in the second part, they ask us to determine the coordinates of 3 points on the straight line. If you remember from grade 9, we take f for x equal, we have the reduced Cartesian y equal ax plus b, and when they ask us to determine the coordinates of a point, we put value for x and we can take, we obtain the value of y, and each time we change the value of x. Here a little bit different. Now since d equal x equal 2m plus 1, y equal minus m plus minus m, and z equal 2m plus 5. In fact, the coefficient of m here in x is alpha. The coefficient of m here is beta, and the coefficient of m here is gamma. So r1 equal 2 minus 1 and 2. Now, any vector of the form, as I said before, r equal n r1 or t whatever, is also a director vector of d. Of course, n not equal to 0. So if we take r2, which is equal to r1, we double the coordinates, is a director vector of d. We notice that r2 equal 4 minus 2 and 4. This is the second director vector. R3, if it is equal minus R1, in this case n equal minus 1, is also a director vector of the straight line D. So R3 equal minus 2, 1, and minus 2. Now, how we can determine the coordinates of a point A? In fact, if you take for m equal to 0, we obtain A105 is a point on D. What I mean by this, I replaced here m by 0, and m by 0. This is the easiest way. For m equal to 0, we obtain the point x equal 1, y equal 0, and z equal 5 is a point on D. If we take m minus 3, so I replace here m by minus 3, then we obtain x equal minus 5, y equal 3, and z equal minus 1, and so on. Now, they ask us to determine the parametric equations of the straight line D passing through the points A and B. As you know, we need, when you want to determine the parametric equations of a straight line, we need a director vector. Here they gave us 2 points. Okay, this is not a problem. We can determine the vector AB, which is a director vector, in fact, of the straight line D. So, first of all, we determine the vector AB. AB equal minus 2, 1, and 3, the coordinates, is a director vector of D. Then D is written in the form minus 2m plus m and 3m minus 2, 1, and 3 are the coordinates of the vector AB, and we can make use of or the coordinates of A or the coordinates of B to determine here. Here I'm using the coordinates of B, minus 2m plus x of B, y equal m plus y of B, and z equal 3m plus z of B. Of course, if we use the x of B, then we must use all the coordinates of B. Or if we start by using the x of A, we use all the coordinates of A. Now they ask us also to determine the parametric equations of the straight line D passing through the points, through the point A and perpendicular to the plane B, x 3y minus 2z plus 1 equal to 0. Now, since D is perpendicular to P, then n, which is a normal vector of the plane P, is parallel to the straight line passing through A and perpendicular to the plane. As you see here, if I have a straight line perpendicular to the plane, then it is parallel to the normal vector. The normal vector in this case is a director vector of this straight line. So I can make use of n as a director vector of the straight line D. Now, as I said, n is a director vector of the straight line D, then this is alpha, beta, and gamma, and we make use of the coordinates of the point A, with 2, minus 1, and 3. These 2 questions are for you to solve. And also this question is for you to solve it. Now, to prove that a point A lies on a straight line D, it is enough to replace the coordinates of A in the parametric equation of the straight line D. Example here, if we have a point and they ask us to prove it that it is a point of the straight line, we replace the coordinates of the point A here instead of x, y, and z. If we obtain the same value in the 3 equations of D, then the straight line lies, and this point lies on the straight line. Example. Here, they gave us the straight line D of equation x equal t minus 5, y equal 2t minus 1, and z equal t plus 2. They ask us if the point A is on the straight line D. First of all, what I'm going to do, I'm going to replace the coordinates of the point A in the parametric equations of the straight line. We obtain in the first of all, minus 3 equal t minus 5, then t equal 2, the second one t equal 2, and the third equation gives us t equal to. Since the three answers are compatible, so I can say that A belongs to D. Now, in the second part, they ask us to check up if B is on the straight line B. Now, we replace the coordinates of B in the straight line, so we obtain minus 2 equal t minus 5, then t equal 3, and here t equal 2. There is no need to continue for the third equation. Since the first two equations gives us different values of t, then B does not belong to D. This question is for you to solve. That's all for today. Thank you.